name is Elijah Martinez, and I'm a part of Group 1 at 8:30. And this is our lab report for Lab 2. In this lab, my group and I will be going over one of the most fundamental ideas in physics, and that specifically is how objects move. We will be studying the relationship between position and time using a position sensor and a air track. With this setup, it allows us to observe motion in its purest form without the interference of friction or irregular surfaces. In physics, this experiment is typically used to demonstrate a phenomenon called uniform motion. This is when an object moves at a constant velocity, and also form acceleration, where the velocity changes at a constant rate. Because the air track reduces friction so effectively, the glider's motion closely resembles the idealized graphs, basically making it easier to see the patterns often resembled by motion equations. We use this type of experiments in physics because it helps confirm the theoretical relationship between acceleration, position, and velocity. In real life, these theories apply to everything that we see, such as cars moving on a highway, or even astronauts going up into space. Engineers, for example, rely heavily on position time data, analyze traffic flow, and even plan satellite trajectories. By studying this kind of motion in a controlled environment, such as a classroom, we can better understand how objects behave in the world around us and why accurate data of position and time are essential in science and technology. I will now hand it over to Daniela, where she will better explain all the materials that we used in this lab and how we use that to carry out with our calculations.
Hi, my name is Daniela, and now I will explain the materials we use for the lab number 2. For this experiment, we use an air track system with a glider, and the air track allows the glider to move with very little friction, which helps us analyze its motion more accurately. We also use an air pump. The air pump pushes air through the track so the glider can float slightly above the surface. This reduces friction and ensures smoother motion. Another important material was the motion sensor. The sensor detects the position of the glider as it moves along the track. This allowed us to create a position versus time graph. We also used a computer with the capstone software. This software recorded the data from the sensor and automatically generated graphs. It helped us analyze the slope of the position versus time graph to calculate velocity. Additionally, we use graphing tools inside the software, such as the multi-coordinated tool and a statistical tool, to select key points like the initial position, turning point, and final position. Overall, each material was essential to measure the glider's motion accurately and to calculate its velocity. Now, I will pass it to my teammate to explain the procedure.
I will be presenting the procedure for lab number 2 and the activities. First steps first, equipment setup. We begin the experiment by making sure that our equipment is balanced and set up correctly. We set up a glider and we set up a motion sensor. If either of these are incorrect, we will get inaccurate readings. So to start up, we set up a frictionless slider. At the very middle of it, we set up a weight that will go from left to right side, ensuring movement and velocity. After that, we would open up our software, which is tied up to our motion sensor, and we would document the entire procedure, and we would check out the length of the track as well as the speed of the weight. Each one of these graphs was divided into each one of our classmates. One person did one graph, the other person did the other one. Each one of these took roughly about 5 seconds to create as a document, or take a look at this graph right here. as it is approaching a decline right here, that means it is approaching the motion center. As it's approaching upwards in an inclined motion, it is showing as a gliding away from the motion sensor. This will be the same for all of these, with the exception of 3. 3 is cut a little bit short with 10 seconds, showing that it is a much faster rhythm of speed, or at least very short cutoff time.
The objective of part 1 was to find and record the time and position for the initial position, the position of change in direction, and the final position. For our graph, the data showed that the initial position was at 0.19 meters at 1.2 seconds. The change in direction took place at 1.63 meters at 2.95 seconds. Lastly, the final position was back at 0.19 meters at 5 seconds. For step 2, we are tasked to find the change in position in meters, the change in time in seconds, and the velocity in meters per second. For point A to point B, the change in position was the final of 1.63 minus the initial of 0.19, which equaled out to 1.44 meters. For the change in time, the final was 2.95 seconds minus 1.2 seconds, which came out to a total of 1.75 seconds. Using those two numbers, we divided 1.44 meters divided by 1.75 seconds, which gave us a velocity of 0.823 meters per second. For point B to point C, the change in position was the final, which was 0.19 minus 1.63, which gave us a total of negative 1.44 meters. For the change in time, we did the final, which was 5 seconds, minus 2.95, which was the initial, which gave us a total of 2.05 seconds. For velocity from point B to point C, we used negative 1.44 divided by 2.05, which gave us a total of negative 0.702 meters per second. For step 3, we drew out the following graph that shows how the line looks when we increase our y-axis value, how the line looks when we decrease our y-axis value, and how the line looks when the y-axis value stays steady. For step 4, the values we received were a mean velocity value from point A to point B of 1.02 meters per second, and from point B to point C, the mean velocity value was negative 0.73 meters per second. Lastly, for step 5, we used the values received from step 2 and step 4 to find our percent difference. From point A to point B, our mean velocity value was 1.02 meters per second, and the hand computed velocity came out to 0.823 meters per second. Using the percent difference equation, we put 1.02 minus 0.823 over 1.02 times 100, which gave us a total of 19.314%. For point B to point C, we had the mean velocity value of negative 0.73 and the hand computed velocity of negative 0.702 meters per second. Using the difference percent equation, we put negative 0.73 minus negative 0.702 divided by negative 0.73 times 100, which gave us a total of 3.836%.
Oh wait, that's actually, yeah. What the fuck? Ready? Go. Yep.